Hello, I'm Philip Hughes, and this film is part of a series about analysis of survey data, quantitative data, and this film is about looking at bivariate analysis. Bivariate analysis means looking at two variables at a time. It's the sort of analysis that you do when you're looking at how different groups of people vary on a particular measure. In this sort of analysis, we can also begin asking whether the differences between the groups of people are likely to apply to those groups in the wider public. Again, the statistics that we use, the way that we do our analysis, depends on the type of data that we're handling. If we're looking at nominal data by nominal data, for example, the most common form of bivariate analysis in surveys is cross-tabulation. Go to the Analyze menu in your statistical program and then to Descriptives and Crosstabs. You can then enter the two variables you want to compare. Suppose we want to look at how people were employed during the week by their age group. We enter one of those variables into the rows and the other variable into the columns. We must then decide what percentages we want to look at. Do we want to look at the percentages of young people and what they were doing? In this case, the column percentages. Or do we want to look at the percentage of all those working and what ages they were? The row percentages. We may want to look at both, so we can interpret the results either way. We then choose the statistic that we want. For nominal by nominal data, we will want chi-squared and a contingency coefficient. What we have in the results are the numbers in each cell and also the row and column percentages. So we can read those off. Of all people in full-time work, we find that 36% were aged below 35 years. 53% were aged between 35 and 54, and 12% were aged 55 or over. But we might want to compare the rates of full-time work in these different age groups. In that case, we look at the percentages, the row percentages. So of all the younger group, 35% were in full-time work, compared with 43% in the middle age group and 11% in the older age group. Down below the table is the contingency coefficient, which tells us the general strength of the relationship between these two variables. Coefficients can vary between -1 and +1, with 0 meaning there is no relationship. -1, of course, is a negative relationship, +1 a positive relationship. Coefficients of less than 0.1 or -0.1 are very small and suggest almost no relationship. A coefficient of between 0.1 and 0.3, plus or minus, means there's a small relationship, and in social surveys a relationship of 0.2 is sometimes worth investigating. A coefficient of 0.3 to 0.5 is a moderately strong relationship, and a coefficient of 0.6 or above is quite a strong relationship. Of course, coefficient of 1 or -1 is a perfect relationship, positive or negative. Remember that coefficient means that there's a relationship or an association. It doesn't mean that one factor is causing the other. The other figure we may want to look at is the chi-squared figure. and it's based on a calculation as to what the expected value would be in each cell if there was no association between the two variables. It takes into account the number of cells in the table, which is represented in the statistics at the bottom in the degrees of freedom in the table. The significance is often the most important figure for us here. If the figure is 0.01 or smaller than that, it means that we can be 99% sure that the two variables are significantly related, and we would expect to find a relationship in the wider community from which the sample was drawn. It means that we can reject the null hypothesis that there is no association. It's common to look for chi-squared figures of 0.05 or less, giving us 95% certainty, and to describe this as being statistically significant. If we're dealing with ordinal data, cross-tabulations are also used, and much of what we've said about nominal data also applies to ordinal data. However, the coefficient measure is different. It's common to use Spearman's correlation, or gamma, to measure the strength of the relationship between the two ordinal measures. Again, while Spearman's correlation and gamma are calculated differently from each other and from contingency coefficients, they are interpreted in a similar way, with 0.3 being considered a moderate association and 0.6 or more or greater a strong association. When we're looking at two variables of interval data, cross-tabulation tables are usually too large to make any sense from them. We usually use bivariate correlation. And one of the advantages is that we can look quickly at a range of variables and how they interact with each other at one time. The correlation has a similar interpretation to that of the cross-tabulation correlation. But we must decide if we're looking for relationships which go in one direction only, in which case we look for one-tailed tests of significance, or may go in both directions, in which case we use two-tail tests of significance. Here's an example of a table of factors important to people in making a choice of occupation. We find that there was a moderate relationship between earning money, enjoying people, and extending their skills as factors that were important in that decision. In each case, there was a moderate correlation of 0.4 or above. There was actually a strong correlation of 0.65 between people putting down that they enjoyed people as part of their choice of occupation and extending their skills. But there was a weaker correlation between earning money and choosing a job because it contributed to the lives of others, a correlation of just 0.28. And quite a weak relationship between choosing a job which earned money and choosing a job through which one could live out one's values, correlation of just 0.17. This all suggests that people who look for a job which pays well may be a different group of people to those who look for a job in which they contribute to the lives of others and through which they live out their values. Interval data, binomial or ordinal data, is different again, and the usual way of doing this is by the comparison of means. Go to Compare Means on the Analyze menu, and then it's best to go to One-Way ANOVA, as this will compare the means and provide you with a statistical measure of the significance of the comparison. This will give you a mean score for each nominal category. For example, if we look at the importance of earning money by age group, we find mean scores for its importance for each age category. Rather than chi-squared, we find an F-score, which measures the extent of the difference between the means. The significance value is interpreted as other significant tests, however, and we look again for a value of 0.05 or less to indicate significance. Bivariate analysis shows us where there are associations. For example, the association between age group and the desire to earn money. But it doesn't tell us why. It doesn't show the cause. We find, in fact, from this survey that young people are least interested in finding a job which earns money. But is that a result of age itself or other factors? It's probable that they're less interested in the money because they're unlikely to have children at this stage who are dependent on them. It's also possible that they may not have the demands of a mortgage. To get closer to the actual cause, we need multivariate analysis, and that will be the subject of our next film.